In about 100 trillion years, the last star in the universe goes out. No explosion, no collapse. A single dim red dwarf, the runt of the cosmos, fading quietly into a darkness that will never light up again. And here is the part almost nobody tells you. That moment is not the end of the universe. It is barely the end of Chapter 1. After the last light dies, the cosmos keeps going, into eras so strange that physicists had to invent new names for them. An era where the atoms in your body may simply dissolve. An era where the last structures left in the universe are black holes, until even they die. And a final state so empty that nothing can ever happen again, anywhere. None of this is guesswork. In 1997, physicists Fred Adams and Gregory Laughlin calculated the future of the universe from today out to 10 to the 100 years. This video is that map. And stay for the ending, because one scenario on it could skip the entire timeline and finish everything tonight. To read the map, you first need to know where we are on it. The current age of the universe is 13.8 billion years. Star formation has been happening since the first stars lit up about 200 million years after the Big Bang. The rate of star formation peaked around 10 billion years ago and has been declining ever since. We are already past the bright peak. The universe is, in cosmological terms, middle-aged and starting to wind down. The Sun is a typical main sequence star. It has been fusing hydrogen for about 4.6 billion years and will continue to do so for another 5 billion. When it exhausts its core hydrogen, it will swell into a red giant, then shed its outer layers and collapse to a white dwarf. A white dwarf is a degenerate object, Earth-sized but with the mass of a star. It cools over trillions of years and emits less and less light. The Sun's full lifespan, from formation to faded white dwarf, is roughly 10 billion years.
Red dwarfs, stars smaller than about half a solar mass, are different. They burn their hydrogen much more slowly, and they convect their interiors completely, so they have access to their entire fuel reservoir rather than just the core. Their main sequence lifetime is estimated at hundreds of billions to trillions of years. The longest-lived red dwarfs will still be fusing hydrogen 100 trillion years from now. That is the upper bound on the Stelliferous Era. During this era, new stars continue to form as long as there is dense neutral gas available. But star formation removes gas from the cycle. Most of it is locked into stellar remnants, and the rate slowly declines. By 1 trillion years from now, the rate of new star formation will be negligible. The galaxies will be glowing more faintly each million years as the high-mass stars die out one by one, and only the dim, persistent red dwarfs remain. By 100 trillion years, even those will be gone. After that, the universe contains a population of cold remnants, white dwarfs cooling toward absolute zero, neutron stars rotating in the dark, black holes accreting almost nothing. The light will be over. The matter will still be there. This is the transition from the Stelliferous Era to the Degenerate Era. The Degenerate Era is dominated by stellar remnants, white dwarfs, neutron stars, and black holes, slowly losing energy to the surrounding cold cosmic background. There is no new fusion, no new starlight. The only sources of energy are residual heat from previously formed objects, occasional mergers of remnants, and one extremely slow process predicted by particle physics: proton decay. The standard model of particle physics
does not explicitly require protons to decay, but many extensions of it, grand unified theories that combine the electromagnetic, weak, and strong forces into a single framework, predict that protons should be unstable on extremely long timescales. Estimates range from 10 to the 34 years to 10 to the 40 years for the proton lifetime, depending on the specific extension. Experimental searches at the Super Kamiokande detector in Japan have so far placed a lower bound of about 10 to the 34 years on the proton lifetime. The decay has not been observed. The lower bound is consistent with theories that predict proton decay on longer timescales.
If protons do decay, then on timescales of 10 to the 36 years or so, every proton in every stellar remnant slowly converts into lighter particles, positrons, neutrinos, photons. The white dwarfs evaporate. The neutron stars dissolve. Only black holes remain, because they have no protons in the conventional sense. They are space-time geometry that traps the equivalent. If protons do not decay, and this remains entirely possible, then the Degenerate Era extends much longer, dominated by random rare events, like white dwarfs colliding to occasionally produce a Type Ia supernova. Even these become extraordinarily rare on timescales of 10 to the 30 years or more. Either way, by the end of the Degenerate Era, the universe contains essentially only black holes and the faint diffuse radiation of decay products. The visible structure of the cosmos has dissolved.
The black hole era then begins. From roughly 10 to the 40 years to 10 to the 100 years, the only remaining structures are black holes. They are not eternal. Stephen Hawking showed in 1974 that black holes slowly emit radiation due to quantum effects near their event horizon. The emission is extremely faint for any black hole formed from stellar collapse, billions of years of waiting for a single photon. But over sufficient time, even the largest black holes evaporate completely. A black hole the mass of a galaxy takes about 10 to the 100 years to evaporate. That is the time horizon of the black hole era.
After 10 to the 100 years, the universe enters the dark era. There are no stars, no degenerate remnants, no black holes. The cosmos contains only an extremely thin sea of photons, neutrinos, and electrons and positrons drifting at vast distances from one another. The temperature is near absolute zero, but not quite at it. The expansion continues. Particles drift further apart. The universe becomes asymptotically, perfectly homogeneous, and perfectly inert. This is heat death. The technical name is the state of maximum entropy. The thermodynamic definition is that no organized process can occur because there is no longer any usable temperature gradient between different parts of the universe. The reason the term sounds counterintuitive is that heat suggests something hot. But heat death does not mean the universe is hot. It means the universe is uniformly distributed. No concentrations of energy can flow anywhere because all parts are at essentially the same temperature. The second law of thermodynamics, entropy of an isolated system tends toward a maximum, is one of the most robust statements in all of physics. It is the reason eggs do not unscramble themselves, and the reason a cup of coffee cools but does not spontaneously reheat. Applied to the universe as a whole, it predicts the trajectory the cosmos is on.
The trajectory ends in heat death. Not because anything dramatic happens, because eventually, nothing dramatic can happen anywhere. There are scenarios that could short-circuit the heat-death timeline. The false vacuum decay scenario, a quantum tunneling event that converts the Higgs field to its true vacuum state, could happen at any time, including tonight, although the calculated probability per year is essentially zero. The Big Rip scenario, in which dark energy strengthens over time and eventually tears apart galaxies, then stars, then atoms, is a possibility if dark energy is what cosmologists call phantom energy, which observations so far do not support, but do not rule out. Both of these would end the universe much earlier than heat death, and in much more violent ways. Heat death is the slow, default, statistically inevitable outcome if no dramatic physics intervenes. It is the outcome predicted by the laws we currently understand.
The 1997 Adams-Laughlin paper that mapped this timeline ran the calculations from the present day to 10 to the 100 years and beyond. The conclusion was simple. If general relativity holds, if particle physics scales the way it appears to, if the cosmological constant remains constant, then the universe has a long, quiet end. It is not violent. It is not sudden. It is the absence, gradually completed, of everything that ever made anything happen. The unsettling thing about heat death is not the timescale, which is so far beyond human meaning that it might as well be infinity. The unsettling thing is the inevitability. Stars going out, one by one, over scales so vast that civilizations rising and falling thousands of times do not register. Black holes shrinking, photon by photon. A cosmos that began with the Big Bang, ending with a state in which nothing can begin. That is what the math currently predicts. The next century of cosmological observation will refine the parameters, especially dark energy. It will not change the broad picture. The universe has an expiration date, measured in numbers that the human language barely contains. This was the final video of the Cosmic Mysteries season. From a black hole that should not exist, to a final state in which no light can exist. We have followed what current science says about the most extreme objects and the most unsettling possibilities. The universe is mapped, but the map has edges we have not reached. Next season, we look at what is still being measured.